Have you ever stopped to think about something kind of wild? How do scientists actually work with things they can't even see? I mean, atoms, the tiny building blocks of literally everything. Well, today, we're going to crack a huge chemical mystery and uncover the one secret that makes all of modern chemistry possible. Let's get into it.
So here's the core problem, right? You can't just, put a bunch of atoms on a table and count them one by one. They're way too small for that. So how in the world did early chemists figure out the exact recipes for making, well, everything? It's basically a detective story, and the first clues, they were found in a very, very unexpected place.
The first major step wasn't about counting atoms at all, actually. It was about this massive light bulb moment. Even though you can't see or handle individual atoms, you can measure their collective weight. And that was the big aha moment. Forget counting for a minute, they thought. Let's just get out the scales and weigh stuff. And by carefully measuring the mass of things before and after a chemical reaction, they started to see these incredible patterns, sort of hidden rules that govern how the universe works.
And what they found was that these patterns weren't just random quirks. Nope, they were actual predictable laws. And once they figured these out, they had the first real clues for how to connect the world we can see and weigh to that invisible world of atoms.
Okay, so the first rule is a big one, and you've probably heard of it, the law of conservation of mass. To put it simply, you can't create or destroy matter in a normal chemical reaction. The weight of all your starting ingredients has to equal the weight of your final products. Nothing just vanishes into thin air. And this is just a brilliant illustration of that. Check it out. You start with exactly 100 grams of this stuff, calcium carbonate. You heat it up, and it breaks down into two totally new things. But when you weigh those new products, you get 56 grams of one and 44 grams of the other. Add them up, and what do you get? Boom! 100 grams, a perfect, balanced equation.
The second big clue was the law of definite proportions. This one basically says that any pure compound always has the exact same recipe, by weight. It doesn't matter if you find it in a lab in London or dig it up on Mars, the ratio of its ingredients is always the same.
Water is the absolute classic example. By mass, water is always about 11% hydrogen and 89% oxygen, every single time. This fixed, totally predictable ratio was a massive, blinking sign that atoms weren't just mashing together randomly, there was a system.
So let's just pause for a second. These laws were game changers, for sure. They proved that chemistry wasn't magic, it was a real science with rules. But, and this is a big but, they only told us about the ratios of weights. We knew the recipe by mass, but we still didn't know the actual head count of atoms in the bowl. We were still missing a huge piece of the puzzle.
Then, the big breakthrough came from a place nobody was really looking. Not from solids or liquids, but from gases. An Italian scientist named Amedeo Avogadro came along with this, well, kind of wild idea that was about to change everything.
And this was it. This was the key, Avogadro's hypothesis. He basically proposed that if you have two identical balloons at the same temperature and pressure, they have the exact same number of molecules inside. It doesn't matter if one is filled with helium and the other with oxygen, same size, same number of particles. This was the very first bridge between something we can measure, like volume, and the number of atoms.
So scientists took this idea and just ran with it. They set up a universal standard. They took exactly 12 grams of a really common type of carbon, carbon-12, and set out to figure out precisely how many atoms were packed inside. This was the moment of truth, the experiment that would finally give them that one magic number they'd been looking for. And there it is, 6.022 times 10 to the 23rd power. It is just a mind-bogglingly huge number. We call it Avogadro's number, and that's the number of atoms in just 12 grams of carbon. This is the number that connects the tiny, invisible world of atoms to our big, macroscopic world. So, okay, we have this absolutely monstrous number. What are we supposed to do with it? You can't just go around saying 6.022 times 10 to the 23rd all day. So we give it a simple name to make life easier. And that name, well, it represents one of the most important ideas in all of science. We call that amount a mole. That's it, a mole. And really, you should just think of it as a word for a number. Just like dozen means 12, a mole of anything, whether it's iron atoms, water molecules, or even basketballs, is always 6.022 times 10 to the 23rd of that thing. It's a really simple idea when you break it down. You don't ask for 12 eggs at the store. You ask for a dozen eggs. It's the exact same logic. Instead of saying that ridiculously long number of atoms, a chemist just says, I need 1 mole of atoms. It's the chemist's dozen.
But here is where it gets truly brilliant. This is the real magic. An element's atomic mass, that's its weight in these tiny little things called atomic mass units, or AMU, is numerically the exact same as the mass of 1 mole of that element in grams. So 1 sodium atom weighs about 23 AMU, and a whole mole of sodium atoms weighs 23 grams. That's the bridge. We just connected the invisible atomic world to a regular old scale on a lab bench. We can finally count atoms just by weighing them.
Okay, so now that we have this incredible tool, how do we actually use it day to day? Well, Chemist came up with a really simple visual guide that puts the mole right smack in the center of everything.
Behold, the Y-map. And honestly, this thing is like the ultimate chemistry cheat sheet. You can see how the mole is the central hub, right? It connects the mass of a sample, the actual number of particles in it, and even the volume of a gas. It's a roadmap for converting between all the essential properties of matter.
And the logic is beautifully simple. Whatever information you start with, grams, liters, a number of atoms, your first step is always the same. Find your way to the center. Convert it to moles. Once you're at the mole hub, you can follow the path to calculate anything else you need to find.
Let's see it in action, real quick. So let's say you know the total number of particles in a sample of CO2 gas. Okay? Following the map, what's your first step? You convert that huge number into the much friendlier unit, moles. Once you have that, you just follow the path on the map over to volume. And just like that, you've connected the subatomic world to a measurement you can actually see and use.
And that's how they did it. That's the secret. The mole solved that ancient mystery of how to count the uncountable. It's this simple but incredibly profound idea that lets us use a laboratory scale as a kind of super-powered atom counter, turning a simple measurement of mass directly into a precise number of atoms.
So why does all this matter? What's the big deal? Well, think about it. Every single thing modern chemistry has given us, from life-saving medicines to the advanced materials inside your phone, is possible because we can count atoms. The mole allows us to be molecular architects, building the world atom by atom. And that leaves us with one pretty exciting question. Now that we can control matter at this fundamental level, what are we going to build next?